dive in. I let Leetcode pick a random easy topic, so let's hope it's actually easy. So this is number 1971. Find if path exists in graph. There is a bidirectional graph with n vertices, where each vertex is labeled from 0 to n minus 1 inclusive. The edges in the graph are represented as a 2D integer array edges, where each edges entry has two entries u and v, and it denotes a bidirectional edge between vertex u and vertex v. Every vertex pair is connected by at most one edge, and no vertex has an edge to itself. So there are no two lines, there's only one line, and there are no self-references. You want to determine if there is a valid path that exists from vertex source to vertex destination. Given edges and integers n, source and destination, return true if there is a valid path from source to destination, or false otherwise. Okay, that actually is kind of easy if we allow NumPy. If we don't allow the NumPy library, then I have to implement matrix multiplication by hand, which sounds kind of horrible but also intriguing. Unless there is a different way to solve this other than creating self-multiplications of the path matrix. If you have no idea what I'm talking about, that is totally fine. Okay, well, yeah, I guess we can just do one of the search algorithms, like depth first search or breadth first search or whatever it's called. I guess if we do that, that should be fine. We just need to know if there is a path, so just find all the connected ones. Boom, done. Okay, let's copy this code. I have copied everything over to VS Code so we can do some quick experimentation. Like, how big is n normally? 10 to the power of 5. That sounds rather like a lot. I am doubting myself so hard here. Let's just solve this and then we will see if there is a better solution at the end, and it will be a learning opportunity, right? So I would say we do the nodes are basically just range and Okay. And now nodes is a graph node with I for I in range n. Okay, and now for edge, we can immediately get the values out of one edge. We iterate through the edges and we put them onto both, right? So we add the edge to the one side. We want them on both, yeah, because they're bidirectional. Okay, so nodes of edge source, at neighbor, edge, destination, and on the other side, nodes of edge, destination. I guess calling them source and destination isn't quite right because it's bidirectional, but whatever. And can we just do like a print real quick? Do a formatted string, say node. Edges do. What was the example? This. Sequence item 0, expected string instance, integer found. I guess this needs to be a string as well. We can arrange that. Do I even need that? Can I just do string of self neighbors? What does it do in this case? Yeah, a normal thing. Okay, I overcomplicated this a lot, but yeah, 0 has edges to 1 and 2, 0 to 1, 0 to 2. 1 obviously has edges to 0 and 2, and 2 has edges to 1 and 0. Okay, let's try this one as well. That seems correct so far. So we have now built a graph which will give us the nodes, and then let's just call it waiting list. And now we start at the source, obviously. So at the start we put nodes, source, neighbors. These are all the ones we want to visit, neighbors of the source queue. And we have already visited the source. And then we will visit stuff from our waiting list. So while length of waiting list is bigger than 0. So I think if I thought about this correctly, to do depth first search, we append on the same side that we take from. So we always take the most recently added stuff from the queue to go deeper and deeper. Otherwise we would take from the other end. Say current node is waiting list pop, and then we get all the neighbors cases and not a list? Why is the current node a list? I guess this already was a list. Integer has no attribute value. Oh my god. So that is not a node. The thing we get from the neighbor list is a neighbor index. And then it returns true. Okay. Was this just an accident though? Let's see if we also did the second one correct. The second example says 0 and 5, and that should be false. That's correct. So we need to implement this into this weird thingy here though. So we have all of this, and then we say, well, we don't print this anymore. Okay. We might be printing this in a bit when I discover that I did something wrong, but yeah, we do all of that nice stuff here. Like this. Don't forget this. Import. And then we need both of these functions. And then we do simply these two lines in our valid path, and we return the result of find destination with a source and destination. Build graph n. Well, that's just a bit obnoxious. So just say edges, graph nodes, source, and destination. Okay. Let's see if we put this all in here. Okay, test cases accepted. It tested exactly the same cases that I did. Well, at least it still works. Okay, let's submit. So, I feel like this was a little bit all over the place, and also we didn't win. So, last executed input 100,000 and a lot of edges. We could check here, but I don't know if this makes anything faster. So, how long does this actually calculate? A long time, that's for sure. So what we could do, of course, is like don't check at the very end, check in between, and then if it's not the last one in the waiting list, this is faster. However, if it's the last one in the waiting list, we don't win. Okay, so it finished loading and it takes almost a minute. So let's see if for this particular one it helps if we do if destination equals current node Right, but is it the building? How long takes the building of the graph? Is that a factor? No, the graph nodes are basically knotted. They go super fast, so it is the search algorithm. I mean, we can already check when we add them to the waiting list, right? Does this help at all? Oh, we got a response. I didn't check though. If it's false, all of the stuff that I'm doing right now doesn't help because, like, we're basically just implementing early stopping, but if it has to go through the whole thing, that doesn't help. Oh no, it does find it, but only after 53 seconds. I mean, instead of, like, this search takes a long time, right? We can just check for one. If this list is like super long, then this takes a long time to search in the visited nodes. So what we do is we self-visited false at the start, and then we can skip this and just say nodes source visited is now true. If I could write, this would help. And then we say nodes current node visited is now also true, instead of appending, and then we check for nodes neighbor index and not visited, and the waiting list. I don't know if that's long, but okay. Return destination nodes of destination visited. True, false. Okay, these are still correct. And then redo this. Did it just... what? 0 seconds. Okay, I guess that fixes it, huh? So let's try this again with the visited attribute. So just run this, see if it still works. Yep, and now submit. And it will check everything again. Hopefully it doesn't time out. I guess this is one where it's like false, right? Okay, let's insert this. So source is 0, destination is basically the whole thing, and then how long does this take, and is it true or false? Thinking about what could be the problem here. So if the waiting list becomes incredibly long, then we have the same issue that we are searching in the long list every iteration. So first of all, it goes through all of the edges because there is no match. You can't reach 100,000 from 0 apparently. So, I can delete this by the way. This too. Just do it in here. So for that part I will print no, it's always just 2. I mean, I haven't looked at the edges, but I assume it's basically like a huge circle. Oh no, here we go. Oh, okay. Yeah. wasn't long, and now it's slowly working its way through the waiting list. Right. So now this is taking very long. If the destination is the neighbor index, return true. This can go out here. Is this even possible? Let's think real quick. I mean, we avoid going to the same node twice by checking if it has been visited before adding it. But if it's in there twice, I don't think that does a lot, right? Let's just, I don't know, let's just try it. I don't think it matters. It makes the waiting list a bit longer, but it avoids checking, so that should be good, right? True, false. And then this one here. I mean, now we print this whole thing. That is way faster, and if we should not print this. True, false, perfect. And now this. It was like 16 seconds. What is it without printing? Does it even make a difference? Probably not. Okay, 15 seconds. Is that fast enough for Leetcode? Let's see. Run the code again. Accept it. Submit the code again. How much time do they give you? No. How fast does it need to be? Time limit exceeded. Well, from 50 to 15 seconds. I was quite proud of that. I felt so good about this. Damn it. What else do we have? Avoid going through the neighbors, right? If it already has been visited. So if node of current node visited, then just continue with the while loop. Oh my god. Yeah, I think I just overlooked this before. I have to check at the wrong thing. I check this, but I also need to check if the current node is visited, because now I put extra stuff in the waiting list and I want to notice this as soon as possible. I forgot that part. Here we go again. Run and submit. We made it. It beats. Oh, the runtime is bad, but the memory is really good. I do wonder what other people did, but this already is an hour long, so I will never find out. Feel free to check the solutions for this on your own if you want to, but I will leave you here. Given that this was easy, I feel like I have some practicing to do, but it was definitely worth it to build the tree node thingy, because otherwise we just wouldn't have been able to do this, I think. So yeah, it was worth it to learn tree search stuff, graph search stuff in university. Clap, clap, clap. A few years later, we still use this. I hope you learned something from this, and I hope it was relaxing, entertaining, and thank you so much for watching, and I'll see you in the next one. Bye.